Now, what I'm trying to do in this series of lectures is give you an idea of what the applications are, give you an idea what the algorithms are, but also I'm trying to give you a way to implement them easily, which means I'm also trying to give you an abstraction. Okay? So just as you know what I said, that distributed computing is different from networking in that it provides abstractions, higher level abstractions. Okay? So we don't want to just deal with low level primitives. We want to deal with high level primitives, and these high level primitives help formalize what we're doing also. Okay? When I have an abstraction, I have a good idea. I have a good idea what the underlying design pattern is also. Okay? If I have an input-put abstraction, I know what the communication pattern is. If I have an output-put abstraction, I know what the communication pattern is, which is different. Okay? So what's really going on? How can I provide a programming abstraction to model consistency? Okay? And this abstraction may be implemented different ways depending on what the algorithm is. Okay? So let's go and see what's going on. We have multiple versions of some object, O1, and they can be O1, O2, O3, multiple values object can be replicated, can be there. And I could just go and model this as, I could just model this as an assignment. So I've made now O1 equal to value, I've assigned to O1 value 1, 2. Okay? But it's not been assigned to the other variable. So I can't model this as a local assignment. Okay? We know what local assignment is, something that the programming language gives us. I cannot model it as that. Okay, I can say, well, there's some port P, and I send the value 1, 2 to it, and the other guy does P dot receive into a buffer O1. So at this point, O1 becomes value 1, 2. So that is a remote assignment abstraction, which we saw. But that doesn't model what we want. We want both values to be changed as one operation. Okay, so what I need is a replicated assignment. How do I model a replicated assignment? As an abstraction. And when I say replicated assignment, we're talking about replicating a particular assignment, not replicating the whole process necessarily. Okay? So these are coupled processes, they may not be full replicas. That's important. Okay? And the state shade may be a command, it may be a value, maybe a snapshot, or it may be a command. And a command is neither procedure call. So this remote assignment is also a this replicated assignment can be also thought of as a replicated procedure call. Okay, because we are allowing these values to be commands. Okay? Okay. So this is replicated RPC. So we don't really have an abstraction, no programming language, well, I shouldn't say no programming language, but at least the classical programming languages we use don't give us an abstraction for replicated assignment. There are some languages that have replicated assignment, but they don't have a way to play around with the consensus algorithms there, or even have consensus algorithms behind. So we are going to build an abstraction that has got a consensus algorithms behind it. Okay, so let's create that as an object. Okay, just as a port is an object with some operations like send and receive, we'll create a consensus mechanism as an object, as an interface right now. And the value of that, the value that we are going to synchronize, that could be some parameterized type. Okay, so we could have consensus mechanism for integer, another consensus mechanism for string, or for an image, whatever. Okay, so we don't care about what is being synchronized. Okay, that's something we'll take as a type parameter. Okay, so let's try to derive the operations that you might want to execute on this mechanism. What would you want to do? In the distributed consensus, what operations might you want to have on this? Yeah, Nick?
Propose a change.
Propose a change. Very good. Okay. Anything else?
Get a value. Like get a value.
Get a value. Okay. Setter and getter. So we are not calling it setter and getter. He called it propose rather than set. I like that. Why propose rather than set? It's not guaranteed that it's going to happen, or that's the if. And what else is not guaranteed? So there's the if, and so when I do a set, when does it happen? Immediately, synchronously. This may take some time. So now you've got a get, and he's got to propose. We know propose will take some time to process. So what should get return while it's being proposed? Sorry, you should block. Maybe you want to block. Yeah.
Depends on when you call the get. If you call it before the change, you will get it instantaneously. Otherwise, in some cases, you have to do a wait until the change is turning to basis.
Okay. So the wait operation that you're talking about would wait only if it needs to wait. Okay. Otherwise, it would just return. Otherwise, it would. Okay, so wait is you need multiple threads and you need each thread to do waiting. What's another way of getting data without waiting? Polling. So polling, that means I keep checking gets. I keep checking doing the gets and saying if the get is null, then I'll go and do it again. Okay, not a very good idea, but polling is an alternative. So polling is one method. If you go back to Zemu receive clear was a polling receive. Receive synchronous, there's a receive synchronous. Is there any other kind of receive that we've seen that could, yeah, John?
Well, an asynchronous receive with like
A callback, a listener, which is what Gypsy has, right? That you have a receive listener. So we've got now some operations. Okay, we can get consensus state. Okay, we can wait for consensus. Okay, and we'll go and assume that each propose has some proposal number associated with it. Okay, we can figure out whether it's pending or not. Okay, or the particular proposal is pending or not. Which that the polling solution can use that. We can figure out whether some proposal is pending. We can there may be multiple proposals that are pending, multiple threads in our computer that are creating proposals, or proposals being created across multiple processes. Okay. We can get the last consensus state. So if right now it's pending, we might still want to work with the old value. Okay. If my score has changed, I'm playing a game, and it requires some consensus before I commit to a new score. I might be able to see the old score with a sort of blurring of it, saying, by the way, this might be stale, but this is the last value we knew. Okay. And I should have put propose at the beginning, actually. So propose, which gives you back a proposal number. Okay, and propose takes a value that you're proposing, a state type, and returns a proposal number. Yeah. Why is it floating point? Who knows? Okay, why not? What else would you have it? Sorry, an integer. By the way, I played around with this so much. I refactored my code about 4 times with this type. Okay, and I wasn't trying int or short. I was trying float versus double. And by the way, if you want to create a float or a short, Java makes it so hard for you. So a lot of these values shouldn't be very big. So I was trying to be very good here that, let's make them short. But if you take a float and add 1 to it, or if you take a short and add 1 to it, it returns an int or double, and then you have to cast it everywhere. So I went crazy trying to do that. But you'll see a little later why it's a float. Okay. Can anybody think of why I've got it as a float? So the float has got something dot something, right? I encode more information, and I might be encoding the proposal number and the time, or I might be encoding whoever's proposing it. And why would I want to encode that? Maybe you just need that information, or maybe you want globally unique proposal numbers. Okay, so float gives me a globally unique proposal number. Then the question becomes whether the host should be the suffix or the prefix. Okay, and I played around with that also. Okay. But we'll see, yeah.
Why not use a designated class to do this instead of try to code that into
Why not use a designated client to create proposal numbers?
like a designated class to say like
Oh,
class has to
why not create a class, special class for that, which would be a nicer programming method?
yeah, I'm just
Yeah, I want to be able to compare. I want to be able to say less than and greater than.
but you still can.
I can, but it just gets more involved. Okay, and I do want to reduce the amount of data I send. So that's why I was doing short versus float. So this way I don't have to send 3 different variables. Okay, 3 shorts or 3. So that's another reason. Okay, so that's the reason. Okay. Okay, and we're going to have add consensus listener, which goes and has a callback. Okay, so this is a kind of abstraction you guys could have built in your assignment 3, where you did consensus. You did consensus for two different objects, right? For the atomic versus non-atomic, and for the IPC mechanism, they both use the same algorithm. You probably had 2 pieces of replicated code. We could have had one interface with even one abstraction that was instantiated multiple times, and you could have proposed either to one a new IPC mechanism, and to the other one you could have proposed the atomic versus non-atomic mode. Okay, so this gives you a way to have create reusable code, even if it's not a generic abstraction. Okay, but we're going to create a generic abstraction. Okay, and the underlying algorithm, that will be different implementations of this interface. Okay. Right, question so far? And my consensus listener, you can get the new consensus state. You can say, okay, tell me whenever there's a new consensus state. Or, and I don't know whether we need this or not, we can say, oh, this particular proposal's state has changed this way. Okay? So, the new consensus state tells you about what the new state is. The new proposal state tells you, and there are 3 forms of new proposal state. The new proposal state globally, mine or someone's is this value. Then I have one for my proposal numbers, one for remote proposal numbers. Okay? Let me know whenever a remote proposal state changes. Let me know when a local proposal state changes, or let me know whenever any proposal changes. Now, I've got a type called proposal. I was very good, by the way, about creating new types, except for the proposal number. Okay? And I'm being consistent there with the algorithms that I've seen, okay, and the representations they have recommended also. So, why is state type different from proposal type? From proposal state. So, proposal state is another state type I've got. How is that different from state type? Why do I need that, given that I have state? So new consensus state gets called whenever we have consensus about a new state. New proposal state will be called whenever we have consensus about a new state, sure. Can it be called at other times also? When the proposal just came out, okay, that it's a new proposal state of pending, perhaps, we can call, sure. So it can be pending, it can be consensus. What can it be? Any other value also? Rejected, maybe. Okay. We are doing a Travelocity is trying to do a transaction to multiple servers, and one of the servers rejects it. Okay. Now people are divided between whether rejected state is even an interesting event. So no news is bad news in this case, actually. So if you don't hear from somebody, it means that it was not successful. Okay, your consensus listener will not activate, and you won't do anything. But I think it's a good idea to go and let somebody know if there's an end user there that your transaction was, rather than have them poll and wait and say, oh, did it go through or not? Okay, so we've got a consensus listener also. And just to sort of show you how the difference between get last consensus state and get consensus state. So in one case, you just return the value that's being held. In the other case, you say, look, if some proposal is pending, we return null. Otherwise, we return the correct value. just to make this more concrete. Okay? And new proposal state. So whenever there's a new proposal, so somewhere in the algorithm, a method will be called that says, here's a new state for this proposal. Okay? So the algorithm, your consensus algorithm is responsible for calling that. Okay? And once it calls that, we can take care of the bookkeeping situation of making sure that our record shows that that proposal has a new state. Okay? And then notifying whoever's interested. And who would we notify? We would notify all the listeners, right? And we would do a notify all on anybody doing a wait on that. Okay, some people might be doing waits, some people might be looking for notify listeners. Okay, so the wait, we are doing notify all. So here's a use for notify all, and now your wait just keeps checking if that notification was meant for you. So whenever you're going to notify all, you say, well, if my proposal is still pending, then I'll go back and wait. I was not the one to be notified, and otherwise I'm going to just return the value that the proposal state had. Okay, just showing application of some concepts you learned, and showing, yeah. Nick?
So based on your code, didn't you push the wait for consensus, the call for wait for consensus to the clients, to whoever's trying to get started? Why would you want to do that?
The client?
Yeah.
The client might need to wait for the value, right?
Yeah, but why is not built in? Why is that not built into your
If
last slide when you have get consensus state?
Okay, so why is get consensus state not doing a wait? Right? Your question.
Yeah.
And what was Dong's answer? You might want to poll. Okay, so let's be more flexible. Okay, you might want to poll, you might want to get a notification, or you might want to wait. So this is a flexible abstraction. Okay. Okay. So this is making things real. So the next task is, given all these applications and given their different requirements, what is this design space of algorithms we can worry about? Okay? And we'll begin that question by saying, what is the simplest algorithm that you can find for some application here? Okay? And we'll, remember last time I made you guys wait because I had to make this animation? I still haven't gotten to the animation. But I added all these new slides actually before that. So this is, I'm constantly thinking about how to present this. And I still don't know how to quite present it. But I'm, so we will postpone that to Tuesday. But just to let you know that the next task is to come up with the algorithms. We come up with the abstraction, we've come up with the scenarios, and we now want to come up with the algorithms. And the algorithms will go faster. Okay, because you understand the context much better now. The programming context, the application context. Okay. Everybody can see? Okay, good. So what we were doing last time, what we've done so far, is first look at the context. What kind of problems require consensus, right? Then we said, okay, we're going to have, so different problems will have different needs. That was sort of the implication there. And we will try to, or maybe the same application may need different consensus mechanisms at different times. Either way, what we'd like to do is build a general consensus mechanism that can then have multiple implementations. Okay, and we looked at once the interface of such a mechanism. Okay, so such a mechanism is not bound to a particular type of object, so it takes the type as a parameter, and then it had many operations. The intuitive operation was that you propose a value and you wait for the consensus. Okay, that's what Nick wanted. And then we said, we may not want to wait. Okay, there may be only one thread in the application. So we might want to be notified later. So we had a consensus listener also. Then, notification is a nice facility. a simpler mechanism, which I never recommend, is polling. So we'll also allow you to just get the state without waiting. Okay? And we can get the current consensus state, which might be null if the consensus has not been reached, or we might get the last consensus state, which we might want to display to this user with a little, graying of it, saying this is tentative, but it's about to change. And so we came up with some operations, and these are the operations that could fit in one slide. There will be other operations. There are other operations also. Okay, so we've got this type, which is this consensus mechanism. So now we have to implement this type. And we want to implement this generically in an application-independent fashion. Okay? And think of this as going beyond RPC. Okay? We started with NIO, which is very low-level, peer-to-peer. Then we went to RMI, which is high-level. Gypsy was an example of our remote procedure call. But that is still point-to-point. We can come up with an abstraction that is group communication, which I do have. And we can come up with but these are all helping you create distributed objects. Okay, but you're just saying there is some communication among objects. Now we are saying these distributed objects have some replicated state. Given that there is some replicated state, let's come up with an abstraction that just captures keeping that replicated. Okay, so now we don't go and say send operation or send data. We go and say propose. And when we propose something, the listener is invoked. When the consensus is reached, the listeners invoke not only on our consensus mechanism, but also on all the remote consensus mechanisms also. Okay? And that is really important. I mean, if I go and propose something and I want to wait for it, the consensus to be reached, yes, I can do a wait. But the other side doesn't know necessarily that you proposed. So it can just have a listener which gets triggered saying, here's the new consensus state. Okay? And that matches very well with your application, right? That you're doing in your assignment. So think of this as a replicated object. Okay, we're doing replication, and we are now creating a higher level abstraction where we're not doing a remote assignment or a remote procedure call. We're doing what I said a replicated assignment. Okay, and assignment statement on its own is not replicated. Java doesn't know about replication. So we built an object that captures that, and we know that this assignment will not occur instantaneously. So we have all this notion of pending and wait for consensus and so on. Okay. By the way, why would you can imagine that if you're doing polling, you can say is pending my proposal number. Why would I need something like some proposal is pending? Yeah.
You want to make sure somebody else didn't try to change the state, and you want to wait till they're done changing the state.
So one of the problems that we have is that there may be concurrent changes, and we want to avoid concurrency if possible. Okay, especially concurrency we can't deal with. So if we really are caring about that, maybe before proposing we'll go and check, and not propose something if something is pending, and let it get resolved. Okay. Yeah.
If something's pending, should you make the second one pending wait, or just say like no?
So that's a good question. If something is pending, can we force it? Should we force things to not occur? Okay. And what do you guys think? Should we just why give them an option? Why when you do a propose, don't even accept the propose if something is pending. Ramon?
Well, the client is checking can handle that response. However, individually, so you can have different kinds of clients, and based on their implementation, they can handle that. So if they want to send it again later, they can try.
So what Ramon is saying is that this gives the application more flexibility, right? So you guys in your operating system class or in other classes, have you heard of mechanism versus policy? No? So in operating system, scheduling is a mechanism. What policy you use for scheduling is a separate issue. Okay? And systems guys like to be flexible. They say, we deal with mechanism. We'll give you access control mechanisms. Whether you want to allow this kind of access or not is your policy. It's dependent on you. Okay? Who you want to share with, that's a policy. And which do you think is harder, to create a flexible mechanism or to figure out a policy? Sorry.
Flexible, probably harder.
Flexible is probably harder, so the systems guys kind of believe that, and they say, oh, we'll just create a flexible mechanism. It does require a lot of abstraction and thought. Anybody want to argue the other way? Yeah.
Well, one thing with policy is if you create a policy that is for flexible mechanisms, then you could have a lot of like hanging things that might be covered in one policy but not as well in another, I guess.
No, so when I say that, so what you're saying, you're using the word policy recursively in saying the policy is to have flexible mechanisms. No, I'm saying I've given you flexible mechanisms. Okay, so systems guy says, we are the researchers. We'll give you this fantastic access control mechanism. Now you system administrators, the Bill Hayeses and the John Sopkos in this department, you figure out what policy is. I'm saying whose job is harder? The researcher who created the flexible mechanism or the Bill Hayes in the department who has to figure out the policy?
I could see from the policy, from an admin standpoint, you want to make sure it's fair to everybody. So
It's fair to everybody, it gives you good performance. It's really hard because there are no good answers. The systems guys, why they keep saying flexible mechanisms? Because they don't know the answers. If they knew the answers, they would build that in. So it is ignorance that goes and makes them do flexible mechanisms rather than some extra knowledge. So I say that as somebody who has focused on flexibility. Dave Stotts has always said that if the paper begins with the word a high level and flexible, it's probably my paper. Because one of the trade-offs is that when you make something flexible, it sometimes becomes harder to use. So I've been sort of focusing on easy to use and flexible. Okay, but I have come to the conclusion that the harder thing is figuring out what the policy should be, and this is where so systems guys are not normally don't do machine learning unless they're trying to do some network analysis and so forth. But I am right now convinced that the way to go is that create a flexible mechanism, let it be used, let Bill Hayes and other people use it, and let that way it's used automatically determine the policy used by somebody else later coming in. So I think that is, machine learning has a big role to play in this whole picture. Okay. So anyway, yeah, Nick.
does it kind of resonate with a software-defined network mechanism, like in a network system context? So like you wouldn't necessarily define your topology, but you have a software that sort of analyzes traffic and.
Oh, so in fact, so you're saying, can you have these? IBM has a name for this, which I'm forgetting right now. But these systems, especially distributed systems, that adapt based on traffic and say, okay, if it's this kind of, so when performance is a metric, okay, you can build adaptable systems. So for instance, you can go between centralized systems, which with a single server, and replicated systems that replicate stuff based on how many reads and writes are happening, for instance. And in fact, one of my students did a really nice thesis on coming up with equations that figures out what the right performance is and deploys the right architecture. Okay, so we came up with these flexible architectures also, and then he had the work to do of figuring out what architecture to use. So when it comes to architecture, the job is a little easier. But when it comes to security policies and application needs, okay, where can you deal with this consistency breaking or not, it's much harder. Okay, and that's why you need studies, including user studies, to go and see what really happens. And I personally think that those are harder. And what I've found is that even the systems guys, they enjoy the policy results far more than, hey, my buffering scheme is better than yours. Okay, so that's kind of the stuff that people do in mechanisms that I want efficient and flexible and high-level mechanisms. But anyway, we are digressing a little bit. So we've got the abstraction, we've got an API. Okay? We've got some examples. I'm hinting that we're going to need different mechanisms. Okay? And these mechanisms are going to differ in complexity. And the more complex ones and the more flexible ones are going to be more inefficient. Okay? So we'll come up with a bunch of algorithms, and I want to come up with a bunch of algorithms not only because they're suitable for different domains, but also I don't want to throw you the most complex algorithm right away. Okay? I want to derive it incrementally. Okay? So what is the simplest algorithm you can think of for consistency? Okay, by the way, since we're going to spend the next week playing around with boundary conditions in the implementation, we're not going to have a quiz and discuss the quiz afterwards, so I'm not going to have as much class participation. So please, some of you have been participating, but some of you have been a little quiet, so make sure that you all speak too, because the last class participation stuff has to be graded too. So yeah.
Probably simplest is one API, one database, and multiple clients or browsers.
Okay, so you're saying the simplest example is that one master, multiple slaves, perhaps?
Yeah.
Okay? Okay, that's simple. And what algorithm would you have for it? So my propose. How will you handle my propose? I say propose change, I propose a particular change to a particular variable. How would you handle that now? What would you do? And imagine any underlying communication mechanisms. You can imagine RPC or whatever, but just, let's assume that we're going to work with send message to destination, okay? So I'm a master, I'm at site A, my slaves are at site B to some set of slaves I have, and in the master, I propose a value. And what should propose do? Let me just get Luke because he has it.
Well, I guess you'd change it at the master, and then the slave nodes would pick it up.
How and what do you do? How does slave pick it up?
I mean,
just be a little explicit. So I have to send a message to the slave.
Yeah, force a refresh on the slaves to pull the change, or you could do it lots of ways.
Okay, so they don't know when I'm going to make the change, so it's better for me to send the message.
Right.
Okay, simple. I multicast the message to the slaves. Simple algorithm. Okay, so let's go and see what happens here. We are going to just keep track of proposals. We don't need proposal numbers till the last algorithm I'll come to. Okay, but we're just going to deal with, since we have proposal numbers and we might want to do some logging. So I did a propose. Okay, so we want to get a proposal number. We don't need it, by the way. Okay, as Luke's algorithm did. And we're going to propose that proposal number with the value. Okay, so this is the generic thing we'll do for all algorithms. Okay, so the interesting thing is what happens in the second step. And the get proposal number also may be flexible. Ultimately, when we finally use proposal numbers, we might use them in different ways. So the right thing to do is come up with a factory that creates proposal numbers for you. Come up with an object that is chosen through a factory. So the first step will be flexible. The second step will be flexible in different algorithms. But the idea that we get a proposal number and propose is we'll keep that constant in all our algorithms. Okay? So, and the fact that we proposed, we'll just do we'll do a logging. Logging is a good idea. We sometimes need the logging. Mostly we don't need the logging. Okay? But since we're building this mechanism incrementally, we'll do this. So in this case, there's not, we'll just record the fact that it's pending right now. And so like I said, these to get proposal number and propose the proposal number. So there's propose without a proposal number. You just say propose a value. It says, I've got a new proposal. Let me go and create a new proposal number for you. And then call propose with a proposal number. And record stuff that I proposed, and we can change that. So the top level method is reusable. The other two methods will change. Okay? And this is overkill for the algorithm that Luke mentioned, but this will help us incrementally evolve our algorithm. Okay? So at this point, our state is pending. Okay, we did that too. And we're going to then send proposal number and value to all learners. Okay? So we said master slave, but these guys may not be slaves. They just may need to know my information. There may be somebody that's just monitoring my state. Okay, so we'll call them proposers and learners. Okay, so the proposer proposed. There's a set of learners, and there is some way we can send the proposal number with value to the learners. We'll use that mechanism. In the implementation, I'm using Gypsy. Gypsy is a group communication mechanism, but I'm going to try to keep my presentation as independent of Gypsy as possible. So I'll always have calls like send proposal, send to learners. And I'll never tell you how the send is implemented, and the send can actually send through sockets and I/O, whatever. Okay? So I'm trying to keep this independent of Gypsy. Okay? So this is my atomic step. I send proposal with proposal number and value to all learners, and including myself. Okay? Because I just made it pending, and I will now, the learner will make the state non-pending. Okay? So this will be a general mechanism. So I didn't go and change my state immediately. I proposed, and I become a learner also. So a proposer might also be a learner. Okay? So the notion that there are people who change, there are people who learn, and they may not be the same set is an important concept. But in our implementation, and in many cases, they will be, the proposers will be a subset of the learners. Okay? And the learners may be mirrors, maybe slaves. Okay? This algorithm is not going to work very well for slaves right now, but ultimately we'll have the learner component in other algorithms also. Okay? Questions? So what will learn do now? I get proposal number value, and there's a verdict thing. I'm just adding an extra argument. Let's ignore it right now, saying with how successful the proposal was.
So I would guess that with a given proposal number and value, then you always reach a certain verdict. That would be
Just ignore verdict for now. Ignore verdict and just say.
You decide to either accept it or deny it.
Okay, so at this point, there's no decision. We're just sending the value across. So, I was trying to incrementally present things. So, yes, the learner is learning a verdict. Learner is not deciding a verdict. That's why the word learner is being used. Okay? So, there will be somebody else who will decide whether that's a good value or not. And when we come to future algorithms, there will be some more components that will decide the verdict. For now, we as learners just learn proposal, value, and verdict. Okay? So, we are given these three values. What should we do?
Could you also just log the proposal number and value too?
And exactly, you're totally with me. We log the value too. We log everything because we like logging, not because we need it for any algorithm right now. Only much later, when we come up with the most complex algorithm, we'll need some logging. Okay, and then we'll say, aha, we've been logging, we can just use the values. But for now, we'll just log it. Okay, so change the consensus value. Okay, and that's what we basically need. And now here's my algorithm. And what do? My propose, this is a propose, so it got a little, I made a lot of changes this morning. So I'll try to remember to fix this, but very first thing I do is I get and set next proposal number. Okay, so based on the last proposal number, I get a new proposal number, and then the last proposal changes. Okay, and this is
Are they just incremented by one each time?
Who knows? Remember, I was using a float, so but that's the simplest way to do it. Okay, there's another way too. I might be given a set of proposal numbers when I come up. I choose the next proposal number from the set. Okay, and that's one of the algorithms that I'm going to talk about. When I keep talking about the most complex algorithm, it's called Paxos. So the Paxos guys, that's the solution they recommended. But that is implementation defines. Okay, so and we don't even need the proposal numbers till we reach Paxos. But yes, we might just increment by one. Okay, and then we'll record the proposal that we proposed. Just because we want to do it, not because we need it for the algorithm. And then we'll do dispatch propose. Okay, so I'm maybe doing overkill with number of procedure calls. Okay? But I'm saying, you know what, the propose may require some indirection, may require some thought. That do I propose here? Do I go to a remote site and propose there? Okay? So there's a dispatch propose that decides that. And wow, I've got a typo in my code too. So this should be local propose, not load propose. So it's saying, okay, we will just do the propose locally, but later we will have a dispatch propose that goes and maybe makes the master propose for us. Okay? So we are just being flexible, and I have to remember to go and correct the typos here. And my local propose says, by the way, learner, the feedback kind is success. Okay, so there's no suspense here, and it goes and says, let me record the fact that I'm sending this learn notification, and then I will send to all the learners the proposal number, the proposer, and this extra useless parameter for now that says, yeah, this is the right value. Okay, later the learner, the value we'll see, the learner's learn may be negative also. Okay, and in fact, in all the algorithms, when the value is negative, the learners don't need to actually even know. Okay, so some algorithms say if it's bad news, don't send it. And if, yes, from a correctness point of view, they'll work, but from a user's point of view, they may not work very well if you don't have you don't even learn as quickly as possible that your velocity reservation has not been made. Okay, if you have to use timeouts in your algorithm, it's not very nice. Okay, so timeouts save some messages, but anyway, that's going to be one of these policy matters. Okay, fine. I've taken a very simple idea and made it very complex by having a lot of intermediate methods, but that's good because we'll subclass and override these methods later. And we override some and not others. Okay? And this is what the learner does. The learner gets the feedback, and it just says, hey, record the stuff. Okay, again, recording. Okay, and I will normally not look into the record steps, that's just bookkeeping stuff, but just to give you an idea what kind of recording you might be doing, I might say, okay, the maximum proposal number I've received in a, see, this is why I don't need comments. My variable names are full sentences. I tried to use smaller names, and I got very confused, and I started making mistakes. I forgot which one was which. So I said, I'm just going to spell it all out so that I don't get confused. Yeah.
Did you meant to use if is pending then?
Sorry?
Like,
Okay.
if it's not pending reason, or
So that's interesting. Nick's getting puzzled by the line, if not is pending, return. So I'm saying if the proposal has already been resolved,
oh, okay, that's it. Okay.
don't bother.
Yeah.
It might be the case that I've already know the answer and I'm getting the answer later from multiple sources perhaps. Okay? Right now there's one person sending me learn, maybe we all just infiltrate, we just propagate what I learn, I send to you, you send to others, so we may have multiple learns.
Right.
So for now I'm just saying, hey, I don't need to learn it again. Okay?
And when we get the multiple learners, we still want to record that there was, and we still want to log it.
Right now I'm not doing it. But you're asking these difficult policy questions. Right now we don't even know what this logging is meant for. Okay, it is received message, so we might want to go and have another variable that says how many I have logged, how many I have received, and how many I have done something with. That gets, so, and that's why coding is hard and building systems is difficult. For now, I'm just saying that this is the kind of nature of the logging we do. Hunter?
From the learner's perspective, how do we determine this?
How do we determine what?
Where it's pending? How do we determine if proposal number is pending?
How do we determine it's pending? So let's think about it. When I proposed it, a proposal got created, right? The state should be what? Pending. When I learn it, when I learn a new value, the state should become what? Not pending. Okay? That's what this is saying, to proposal state. I look at the feedback kind. Okay, I look at maybe the proposal number and proposal also. Okay, I don't really need to do this till Paxos. And I go determine the new state. At this point, it's not pending. It might be successful resolution, it might be some kind of error, but it's resolved. Okay, so it's pending when we haven't received a learn on it. Come on.
So your is pending function takes a proposal state type?
Proposal number.
Oh,
Proposal number.
oh, it does. Okay.
Yeah, proposal number it takes, but my proposal state takes a feedback kind. And if I got success there, then I'm going to put consensus.
Okay.
Okay? You know, I showed you guys the algorithm and I thought a lot about whether I should show you the code or not. And I said, you know, what learning do they have with the code? And this has raised so many questions that I'm very happy that I implemented the mechanism and I'm showing you the code. That's fine. Okay. Okay. So that's my learn algorithm. And feedback kind is for future algorithms. Okay. And again, proposal number is irrelevant to our algorithms till we reach Paxos. Okay, but we're just keeping it anyway. Okay, so this is the algorithm. It is meant for one master and multiple slaves. But you know, let's go and run it on multiple proposals and see what happens to really understand its limitations and maybe its strengths too. So I'm going to run it with 4 processes. All 4 will be learners. Okay, and 1 and 2 will also propose. Okay, and the example I gave you, intuitive example I gave you was a wartime problem. You know, whether we should attack at a certain time or not. We'll do a more general problem here. We are trying to figure out the meaning of life, which, you know, if you're idle waiting for the war orders, you might want to discuss, or even in peacetime. So here's what the listeners are doing. Okay. So the listeners have to go and remember, we've got this meaning of life mechanism is an integer value. Okay, and that's a replicated value now. We all want to agree to a certain value, and we have to create a consensus mechanism for that. Okay, I've hinted that we're going to have multiple consensus mechanisms, so I will use a factory to create that mechanism. Okay, the method that calls the factory will be a factory method. This is all recursive, so I use a factory method to invoke a factory, which will be subclassed later. And I say create consensus mechanism, and you know, all the things below create consensus mechanisms are details of the implementation. Okay, ignore them. That's not an algorithmic issue. You kind of need them for your implementation. But we've got a meaning of life mechanism that we've instantiated, and now we go and attach a listener to it. I haven't shown you the code. Once I've got the mechanism, I can say add consensus listener. And the consensus listener, when a consensus is reached, just prints out a string with a new value. Okay? So this is showing you the abstraction in use. Okay, questions? Okay. So the factory is important. Okay? Oh, we've got to give that mechanism a name that everybody can discover. So we have multiple replicas, and we all should be able to discover the name of what this replicated object is. Okay? So now this is not a distributed object whose name we are advertising. This is a replicated object whose name we are advertising. Okay? Which is implemented using distributed objects. And the point is that in this listener, there'll be a new method called when both remotely and locally when that consensus value changes. Okay? All real now? Okay? And this shows you, I'm not saying this is the right way to do things, because again, I don't know what the right policy should be, what the application is, whether it can handle concurrent interactions or not. But what am I doing first? I'm saying, look, if some proposal is pending, wait for that to be resolved. Okay? Brennan likes that. He doesn't want to create a mess. Okay? But I have the flexibility to not do that. And then I say, okay, at this point I'm going to propose a value. Okay? And I'm going to now poll for the value. I'm going to wait for it to be resolved. Okay? And once it's resolved, what am I doing after that? When I unblock from the wait, what am I trying to do? I'm looking at the state. Okay? We know it's not pending at this point. And what am I doing? If it's not concurrent, it's either error or it's consensus. If it's error, I don't want to try again. If it's consensus, I don't want to try again. But if I was concurrent, I say, hey, let's try again.
How would you unblock if it was concurrent?
Or because the system tells you that it was concurrent. Whenever the system, okay, so how would I unblock when it's concurrent? The question is it concurrent and do I know it's concurrent? At some point the system will get to know it's concurrent perhaps. Okay? If it's checking for that, if it's setting that value, it knows. It may be concurrent and you may not even know about it because your algorithm is so weak, which our current algorithm is. So in that case it won't set to concurrent. It'll just say, oh, success. Because the algorithm is no good. But if it told us it's concurrent, we're going to retry it. Now, is that a good idea that I retry, or should I just maybe not retry it? I should just propose once, and if it's concurrent, say, I shouldn't have proposed that value.
Ideally, you want to retry this, otherwise, I don't know, because if we kick it back to the application, you might decide to retry anyway.
So you're saying, this is the application, by the way. I'm not kicking it back to this is the application code. Yeah, I'm not doing this automatically inside mechanism. This is abstraction use. So I'm asking you guys a policy question. Should you retry or should you give up? It depends on what you're doing. So is there a situation where it makes sense to retry? Think of your example. You're trying to move an avatar. If you're moving in simulation, you're moving.
You might want to not retry this. That would possibly be.
Okay, so commuting operations versus non-commuting operations, and you may not want to move it based on what this concurrent operation was that occurred, or you might say I'm going to move it anyway. My movement and the other person's movement are independent, so I'm just going to try it again. So it depends on how much state correlation there is between what you read before you propose. Okay, so if you don't need to read any new values to propose this value, you say yeah, I'll propose it again. And a lot of these algorithms have this thing. They say retry, but it's not a safe thing to do. Okay, so I'm doing this mainly to go and exercise the mechanism, and to just show you and add concurrency so that we can see what problems occur. But this is not a safe thing to do. Okay, so this is not something you want to do all the time. Yeah.
Is it not safe because if they're non-commuting, you could get a race condition based on like who started first and who, when you retry, you might go.
Okay, so the question is, why is it not safe? One reason it may be not safe is because there may be a race condition. Okay, there was a race condition, and so if there's a race condition, what bad things can happen?
Well, if someone did something and you saw that was happening, so you waited and then tried again, and you just overrode whatever they just finished doing.
Yes. So you just overrode what they finished doing without even seeing what they did. Maybe based on what you saw, you might do something else. Okay? So that is why it's not safe. But it can also not be safe because the replicas diverge, because your mechanism couldn't handle it. So that is not what we're worrying about. We are assuming that the mechanism will make sure that the same sequence of operations occurs. Whether that sequence of operations is meaningful or not is another issue. Okay? So the other person might have deleted an object that you're trying to replace. And now you're getting, index out of bound or key doesn't exist kind of error. Even though we are all getting that error, so we are all consistent, we are all badly consistent, So that's why it's not safe. So I want to just point this out, that many algorithms, like Nick was pointing out, say, oh, just you fail, you just try again. That's not a safe thing to do. Okay? So let's go and see what happens. I propose the meaning of life, and I am proposal number 1. So I change the value to 42. I make this pending, saying this is my pending value. It's not really a committed value. I invoke learn on myself. By the way, this is not necessarily the order in which learns will occur. In fact, when I show you the traces, my learn occurs after the learns in other sites, when we're all running on the same computer, just because of the way things got scheduled. Okay? So I learn 42. So I go and when this learn 142 method is called, what is its effect?
Change it to 42, so it is and
Make it not pending. Okay, 42 is already changed. Now, at the same time, 42 proposed around the same time or before, in this case, proposed 29 was called. Okay, and this was at site 2. They changed their value to pending. Okay, and they called learn on themselves. They called it consensus. So we can already see there's a problem here. Okay, they have diverged because the algorithm is weak. But let's just see what happens now. So the learn will go to some other site. They change the value to 29, and they don't have to. It never became pending, so the value remains 29. It's 29. So now the other propose gets called on another site. They change it to 29. Now this proposed learn comes in. They change to 42. This learn comes in. Change to 42. Okay. So this is how the algorithm works. Works very badly because we have 2 proposals. It was not meant for 2 proposals. Okay. But at least we get to know how it works. And we get to know how learn works. And this learn is going to be used throughout all our algorithms. Okay. Question?
I missed why the third one didn't get overridden for 42.
Sorry, it's a third one. Okay, have you even finished, right? 29. You guys are more active than my brain. Your brain is more active than mine. So it's not an atomic broadcast. This is what you guys implemented initially, right? Well, actually, not quite. Yeah, this is pretty much what you did, assuming well, you went through a server, so it was not quite what you guys implemented. But it's not an atomic broadcast. Okay. And just to show you, this is the output of 1. So I go and send learn notification for 42 to everybody, and then I receive the learn notification of 29 before I receive my own 29. Before I receive my own value of 42. So I say, okay, meaning is now 29. Then I receive my 42, and I say the meaning is 42. Okay, so this is very interesting. This actually happened, that the remote learn notification came before my learn notification reached. Okay, the thread that executes a propose and the thread that executes learn are 2 different threads. Okay, the thread that does learn is the receiving pipeline thread. The one that does propose is the main thread. Okay, and because of scheduling, this is what happened. And at proposal 2, this is not what happened. They sent 29, and then 29, their learn method got called immediately, and then the learn method of the remote guy got called. Okay, so they're both 42. And the other 2 sites, they don't send any learn notifications, they only receive learn notifications, and 42 comes later. So we ultimately have the correct consensus state, which seems to say that 42 is the right value, right? So
if you intentionally run your scheduler so that remote proposals come in before your own, then you have some sort of priority over values that you proposed because yours will overwrite any proposed values you don't.
So I'm not sure I follow completely, but you're saying if you control your scheduler, now you can't really, you shouldn't really be controlling your scheduler. You should be controlling the algorithm.
Yeah.
But and what I did here, I did not try to put any breakpoints, to go and make this slow. So it's not as if I deliberately went and delayed the learn. It just happened so. Okay. Okay. But you're saying so.
I'm just saying you could use that for some sort of priority.
So you could go and. So it's very interesting. We try to reach consensus, and we try to reach consensus without changing the scheduler, without changing the network. If you start changing the network, for instance, certain things may not occur out of order. And there are people who are networking people who say, why do you want to do a distributed algorithm? We'll just fix the network to go and to route things in a different way. And what you're suggesting, and I'm not sure how far we can go there, but the local versus remote is a simpler case. Two remotes is the harder case. And to go in, and if they're both going to be handled by the same thread, then you can't do anything with the scheduler. Okay? And it's better to go and just change your thing. Sam, you had a question?
Yeah, I was just saying you could modify it so maybe the learner looked at whatever timestamp was associated with its current, learns that it's got. And
So you're saying we should use timestamps to compare my time with remote guy's time?
yeah, but that would require you to just sit at some point because you wouldn't execute learns as soon as they came in.
And is there a more fundamental problem with 2 different computers having the same? Yeah.
I think an easier method with some information we already have is the proposal number. If that's getting propagated, then if say 42 was like proposal 1 and 29 was 2, and then you got 42 as the second proposal that comes into you, you don't take it in because you've already processed a proposal higher than it.
Okay.
Or that value.
Okay, excellent. So you guys, I have opened a can of worms here by telling you all the things that are wrong with this, and you're all on the right track to some degree. You can come up with a lower level mechanism to handle the solution. You can use real times to try to resolve this, or you can try to use proposal numbers, which we will use. What's the problem with using real times, Brennan?
Is there any guarantee that there's like some form of like synchronicity between the 2 computers?
So having a global time is an extreme. Yeah, Jacob?
I was going to say that at least I know that Linux and Windows, one of them uses GMT and one of them uses whatever time zone you're in. And so if you dual boot, you have to set Linux to not set your clock to GMT because Windows likes to set it to your local time zone.
Yeah, we can translate between time zones.
But I mean, like, you would have to make sure that.
Yeah, we can do that. Yeah, Nick?
Yeah, so in my presentation for the other class, it was one of the main things that there's no truly synchronized system clock for a data center, or just one data center.
Okay, so synchronized time clocks is very difficult, and Kevin has been proposing that we use satellite time. Okay, we go and we use this clock from some central location to do this.
But there was network delay anyway.
Yes, so it's a can of worms. Okay, but we can use when we go to certain solutions where there'll be centralization, and we can use time then to say which message came earlier.
Yeah.
So we can resolve conflicts by saying in what order they occurred at a particular site, or what their numbers are, as long as the numbers are globally unique. And you guys saw that my proposal numbers were floats, and I suggest and they are indeed going to be unique. So there's all these mechanisms, but exactly, you're on the right track. Okay.
You're using like an external get proposal
It's a proposal. It's a method that is called locally, though. If I start trying to get it from a remote process, then I have to have consensus on that too. That's a proposal ID variable I have to create consensus on. But one way to have unique proposal numbers is what I said, that each side gets a different set of proposal numbers when it comes up. Now we have unique numbers. Okay. That's what Lamport, who invented Paxos, that's the solution he suggests. Okay, we won't use that solution though. Okay, so let's go and see. We've got this algorithm, with multiple proposals creating problems. But of all these scenarios, what is it useful for? So I am a browser trying to go and submit my quiz to Sakai. Will this algorithm work?
You're the only one submitting, right?
I'm the only one submitting? Sure. It's overkill. It has n learners. I have only one learner there. It'll work. Okay. I am Travelocity trying to go and get a hotel reservation. I'm trying to get a plane reservation from 2 different airlines. It won't work because somebody who hasn't answered, please. This today. Okay. Somebody who has answered. Somebody who hasn't answered. Nobody. Okay. So who wants to answer now? Brennan, have you answered today?
I think so.
Okay. So Sam, what's the reason?
It won't work because you'll be double booking in places because you might, reservation might change to a hotel or something like that, and it didn't tell everybody. Someone else who tried to book finds out later. And so after they say, hey, I want to book that. So 2 people want to book a hotel at the same time, but they don't communicate, and then they both try to book, but the message that is booked doesn't come to the other guy.
So what happens, let's take this transaction that I'm Travelocity, and I say I want, I want to go from here to here for this much money. Can it just unilaterally go and send a message to all three sides, hotels, etc., saying, hey, take the value? So there's multiple proposal problem, but what's going on here? One of the proposals will go. So let's say the proposals are all being serialized at Travelocity.
Then it would be okay, I guess.
So they're being serialized at Travelocity, so we don't have multiple proposal problem.
That would be fine. Let's go through a centralized route, relay or whatever it is. So that would
As long as there's only one proposal, yes, it's fine.
yeah, that would take
Everyone else is just on there.
But remember, Travelocity has to contact 5 other sites. Why is it contacting those sites?
If you have, say, a hotel and a flight that are, linked together, and you're supposed to be sold in a package, and you have one user, the hotel books for one proposal, and then books the same flight for another proposal, you could get in some sort of deadlock position where it can't propose, where one proposal is for each book, and then you can't switch it.
So in our algorithm, we just send the learn notification. So deadlock occurs when we wait. We're not waiting. So that is not a problem. Okay, Nick?
The problem I thought would happen was that say Travelocity goes to American Airlines and books stuff, but American Airlines also listens to stuff outside of Travelocity, and those people could, and we can't guarantee those dimension consistency happening at the same time. So when Travelocity goes to check the hotel first, and while it was checking out the hotel, someone else booked directly to American Airlines and booked out the only left ticket, and then Travelocity goes to that plane ticket, wouldn't be able to get it, everything breaks loose, and
Okay, so the problem is this, that Travelocity went and found out what the prices were from all the 5 sites, showed them to you, you said book, and when it goes now to Hilton, it says, no, sorry, that was two seconds ago, right? And in this method, there's no way for somebody to say sorry to the proposer, Okay, and Travelocity might say, Hilton may say yes, but American Airlines may say no. So there is only a learn. There is no way of accepting, deciding whether to accept or not. There's the feedback kind that I was talking about. We need that feedback kind now. Okay, so we can't use this simply because there is no vetoing problem. Way to veto. Okay. And with multiple changes, I mean, we're not going to get anywhere. Locks, again, multiple changes, we're not going to get anywhere. Physical mirroring, Akamai? Many learners, and they're just slaves. They're just readers. Yeah. How about master-slave replication? That I'm the master and the slaves are I'm replicating the slaves. Single master.
Yeah.
Same as Akamai? Brennan?
Yeah, I think it's the same, but I don't think the next one will be.
But can you think of a reason why it's not the same, that you might not want to unilaterally...
Can take over for the master?
Yeah, slave can take over, sure. And when the slave takes over and the master fails and the master comes up, does it need the help of the slave?
Yeah.
We saw it might need the help of the slave.
Yeah.
So why might it not work in that case? Yeah, Matt?
If the master goes down, would you have multiple slave proposals to take over?
Yeah, so that's another issue. We can all decide that the lowest numbered slave takes over. So we can all decide that consensus problem easier. Okay, so in that case, why will this algorithm not work when the slave is going to help with the master coming up?
You can't come back, yeah, and so the slave can't tell master what data it holds. So you can only accept data and change whatever the state holds.
Yeah, but then Sam?
Like maybe a master, there's two slaves. The master shares the state with one person and crashes. Someone becomes the master, but the master and the slave are now not the same. And then when this master comes back up, there's two different states that it can look at.
So if the master dies right after sending the message, but before the message reaches a slave,
Then they're all out of sync after that.
then out of sync, and more important, when the master comes up, there's no guarantee that if they need the slave state, there's no guarantee the slave has that. So this is something that's very configurable in the real systems. Okay, and the answer is yes and no. Okay, if the master just comes up with the log file, you don't have to wait. Okay, but if you MySQL has something called synchronous and semi-synchronous and asynchronous replication, and this is asynchronous replication where there's no shared time at all, so that's. But if you need some more guarantees, then you will go and share with the slave before proceeding. Okay, and of course master, as Brennan was pointing out.